Hello and welcome. I'm going to talk to you a little bit today about quantitative research methods. So we're going to go over a few things kind of broadly of things you need to know if you're interested in doing a quantitative research study. So we're going to talk just a little bit about developing a study question. We're going to talk about how you might think about collecting data for your study. And we're going to talk just briefly about some different analysis methods that you may use to understand the data you've collected. So we're going to jump in with studying with a research question and figuring out what to study. So there's a lot of places where we get ideas on what type of research would be helpful. Maybe it's within the realm of public health, and we want to know what's happening in a specific population. Maybe it's in a clinic with a specific set of patients that we want to help them do better or get better faster, right? So we need to learn some things ourselves before we can even pose a question. So we want to do some research and think about where are we at right now? So maybe we look at some descriptive data, whether that's for a population or maybe it's for a specific disease that we're interested in. We're going to look at what previous research has been done. We're going to search through some current literature and understand what's happening. Maybe we'll attend some scientific meetings and talk to people there or see presentations that spark an idea that we would like to know more about. Maybe there's a data set or some information that's out there that we want to take a look at and say, oh, this is a really good research question. So there's a lot of different ways that we can come up with a research question. I think this is probably one of the hardest parts, right? Is you want to get a really good question, and then you want to figure out what's been done before on that question. So when you develop your question, you want to keep it as simple as possible and state your ideas in terms of a hypothesis. So you want to do something that's important and significant while keeping it not so complicated and not too broad. And that's kind of a fine line to tread sometimes. So we want to figure out what could we do. So one example that I use a lot is maybe we want to do a study looking at vitamin D supplementation during pregnancy and how that might affect type 1 diabetes incidence in children. Right? So our hypothesis would be that increased vitamin D supplementation during pregnancy decreases the rate of type 1 diabetes in offspring. So it takes us a while to get there, but that's kind of where we want to get to. And the first thing we need to do once we have that hypothesis is understand what's been done before. So we kind of write up a background section of previous work that has been done on the topic of interest. This helps us not only understand what has been done before and how we can improve upon it, but also how they did it and how we might conceptualize our study in terms of previous research. And then we need to know, why is a new study needed? What do we still not know? What was left unanswered by those other studies, and what can we do to help? So once we kind of get that preliminary information, then we want to put everything down and start getting into the nitty-gritty of what we're trying to do. So before we start any study, we need to have a really good plan. And a protocol is the study plan that gives you all of the information you need to conduct a study. So we start with our hypothesis. We then move on to our background and justification. And then we move on to a lot of other things that we'll talk about today: study population and recruitment, study design, data collection methods, sample size, statistical analysis. And we won't get to some of these, like ethical considerations, timelines, and references. But this starts to help you formulate, and you start to get these pieces together to understand what your study will look like and what you'll need to do that study. And this isn't exhaustive. You may need other things like a budget, a data management plan, and a data dissemination plan, among other things. But let's start out. Once we have a hypothesis and our background or justification for the study, then we need to define the population. So studies always start with the population, because this consists of who we want to generalize our results to. Like, who do we want to take this information and apply it to? When we do studies in public health, often there's a geographically defined population of interest. In medical studies, there often is. It's generally a little bit more broad, um, but usually to people who can access the type of treatment that you're studying. So when we do a research study, we want to describe factors associated with particular outcomes within the population, but we can't study the entire population, whether this be defined geographically, defined by someone who has a disease. We need to select a sample from that population, and we make inferences about the population from our sample. So we need to find people to participate in our study. So we need to think about our population. Who is this study for? Is it for children? Is it for pregnant persons or persons who may become pregnant? Is it for pancreatic cancer patients? So we need to figure out what is our population? What are we focused on? Once we know that, ideally, we'd recruit a random sample from that population. Um, that's almost never possible. Some public health studies have done things that have tried to get close to that. They have done recruitment from driver's license list for general population, maybe collecting or recruiting patients from a disease registry, right? So if we have a listing of people in that population, we could pick randomly those to participate. But that often isn't the case, right? That kind of enumeration of the population is difficult. The other issue with that random sample is not everyone is able to be found or willing to participate. So we recruit people based on practical issues. And we have some problems with something called selection bias, right? So our sample might not be truly representative of that population. So we have to worry about that a little bit. Let's look at a couple of examples of how people selected subjects for their study. So a couple of studies, one cohort study looking at the Iowa Women's Health Study. Now this one, as I mentioned, recruited from driver's license list in the state of Iowa. They were looking at postmenopausal women was their population in Iowa, age 55 to 69 years. So that's a pretty good way of recruiting and a pretty enumerative listing of those in the population. There could be those individuals who don't have driver's license from the population, but probably not many in a rural state like Iowa for that age group. Another type of study was a cross-sectional study from the National Health Interview Study. So they were looking at the civilian non-institutionalized population of the United States. So in this case, they did a survey sampling design based on small areas of contiguous counties or a metropolitan statistical area. So they really focused on trying to get a representative sample through that geographical assessment. Again, these are more population-based studies, but if you did a clinical study, so for example, if you were looking at designing a study around treatment on children with cancer, then a good place to recruit for that would be something like the Children's Oncology Group that is connected to treatment facilities that treat those children throughout the country. Okay, but we want to always remember that we're trying to get a sample and apply that, what we find with our sample, to the population. And based on that setup, it brings us to our statistical background. So the idea in the statistical setting is that we have a hypothesis and we want to test that hypothesis. So the way that we set this up is kind of in a weird way, right? So we have what we call a null hypothesis. So say we want to do a study looking at incidence of type 1 diabetes in offspring and supplementation, prenatal supplementation with vitamin D. So we think there's going to be a difference between those groups of supplemented kids and non-supplemented kids. Our null hypothesis says there's no difference, right? So that's what we start with. It defines what it means to have no effect, no treatment effect, no exposure effect. So if we have two groups that we're comparing, saying that those two groups are the same. And statistics is set up in that is assumed true unless our data provides us evidence otherwise. So we assume that there's no difference between two groups unless we have enough data to show that there is. And that's our alternative hypothesis. So we want to reject that null in favor of our alternative. So this is what we think might be the case. It can be one-sided or two-sided. So we can say we think the incidence of type 1 diabetes will be lower for those kids with supplementation versus those without. Or we can say there'll be a difference in type 1 diabetes rate between those two groups. Now that two-sided is the one that we usually use because if we found that there was an increase due to supplementation, we would want to know about that as well. So that's kind of how we set things up when we do statistical testing on things. And sometimes we get things wrong with statistics, right? So we're just looking at a sample and we're trying to apply it to this population. So we could get a weird sample, right? And it could not match up with what's actually true in the population. So we do our study and we either reject the null or fail to reject the null. So when we reject the null, we say that there's a relationship or those two groups are different from one another. And when we fail to reject the null, we say that those two groups, we can't tell them apart. We think they're the same. So sometimes we're correct, and that's actually true in the population. Sometimes we're not correct. So we have these two different types of errors, type 1 error and type 2 error. So type 2 error is when there's really not an association and we say that there is. So we say that those two groups of vitamin D supplementation, they're different in their type 1 diabetes rates when really they're not. So that's kind of the error that we hate to do because then we might say, oh yeah, pregnant people should take vitamin D supplementation to prevent type 1 diabetes. And if that's not true, there could be some risks associated with that type of supplementation. The other way we can be wrong is if we say there's no difference between these two groups, but in reality there is. That's a type 2 error. So if we say, we don't think supplementation matters that much, but really it does, well, that's a problem, but it's not quite a big a problem because we'd say, well, supplementation's up to you. So those are the two errors that we worry about. We worry about type 1 error a little bit more. And we refer to that as the significance level, or alpha. So it's the probability of rejecting the null when there's really no association. So this is the probability or how likely it is we'll find an effect of the treatment or exposure by chance. So typically we can choose this and we try to keep it low, around 5%. Type 2 error, we call beta. So that's the probability of failing to reject the null when there's an association. And we have a related value called power, which is 1 minus beta. And it's the probability of finding an association or rejecting the null when an association actually exists. So that's the probability of getting it right. So we want power to be high. Usually we choose it to be about 80%. Now we use this information on our statistical testing to figure out how many people we need to get into our study. So we need to know how many people to include. We want to say what difference is meaningful. So if we see a difference in type 1 diabetes rate of about 5%, would that matter clinically? And that's what we want to base our numbers on. And it helps make sure that we use our resources ethically. So it helps us develop our timeline and budget, and it prevents us from doing a study that's too small that won't provide us anything conclusive. And another benefit, it requires that investigators have a well-specified outcome and planned analysis. So the basics of sample size is we need 5 different things when we calculate it. We need how we're going to analyze the data. That's kind of set by the question. We need our significant level and our power. So we need to know what we are going to tolerate in terms of type 1 and type 2 error. Those are set, right? We usually say, oh yeah, we'll tolerate about 5% type 1 error and about 20% type 2 error, right? Usually we're more worried about making a type 1 error. So those are set by the researcher. And then we have to know something about what differences can we expect and what's the expected variability. Those are estimated from the data or from the literature or using preliminary data. We might also, our expected difference might also be something that's clinically meaningful. So those are the things that we need to calculate the sample size for a study. And changes in each can affect the sample size. So if we want a lower chance of making a type 1 error, then we're going to have to get a bigger sample. If we want to increase our power, so lower type 2 error, then that's going to cost us an additional sample size. If there's a smaller difference between those two groups, we need a bigger sample size to see it. Or if there's more variability, we're going to need a bigger sample size. So we really have to carefully think through everything to come up with a good estimate. Okay, so once we know who we're going to choose, how we're going to choose them, and how many people we include, we want to think about where we're going to get our data. So this is one of the most important parts of a study because we need to make sure the data is really high quality and gives us the best possible information. So if we don't get good quality data, we're just going to waste a lot of money and time. So to think about what's good quality data, we usually think about valid and reliable data. So reliable data are reproducible and precise, right? So we get the same thing every time we measure. Valid data means that what we collect is actually reflects the true values, right? So when we ask somebody how tall they are, and they tell us that actually reflects the true value of actually how tall they are. Okay, so these pictures kind of show you what we want is we want precise and accurate data that is on target for what we hope to measure. So we can have data that's precise but missing what we actually want to measure, kind of accurate but not very precise, and then no precision and no accuracy. So we want both valid and reliable data. So validity, we ask the question, is what we measuring what we think it is? This is hard to determine. There's a lot of different types, sometimes called by different names. So sometimes it's criterion validity. So we compare what we're measuring to another similar scale or another similar item. Sometimes we use face validity, and that's just the question, does it seem to be measuring what it should? Sometimes we bring in experts to ascertain that. And then we can also do predictive validity. If we have groups that we know will be different on these measure, does our measure actually differentiate those groups? So trying to figure out if what we're measuring is actually true. And then reliability asks, does the set of questions measure the same content? And if we ask the question again, would we get the same results? So the first kind of reliability is more about internal consistency, right? So if we have a set of measures, a set of questions that we're going to use as our measure, like a depression scale, are those internally consistent? And then the next question we ask is, if we measured it again, would we get the same result? So if we took your blood pressure 5 times, would we get the same result? If we measured your height or the height of an infant, which can be a little bit more challenging, would we get the same result? So we want to know, if we take the same measurement, would we get the same result? And then we need to worry a little bit about the size of measurement error. So even something like a blood pressure, you might not get the exact same result, but you want to get pretty close. And if it's too far off, then we worry about reliability. Okay, so we want to keep validity and reliability in mind anytime we collect data. And there's a couple of different ways we can collect data. We can utilize existing data. This is called secondary data. So this includes medical records or other data that's collected for something else. So we reuse the data to answer public health or medical questions. The nice thing is that it's pretty easy to obtain. And once we have it, we can analyze our questions. So results are pretty fast. So existing data would include healthcare data, hospital, clinic, medical records, insurance records, laboratory records, It could also include surveillance data, like from state health departments, the CDC, or other disease registries. It could include environmental data. Maybe you're interested in air pollution, um, water contaminants, pesticides, animal data, right? You may get that from different monitoring systems. Maybe you're looking at something in employment record or tax records or sales data. Um, or you can also get data from previous studies. So there's a lot of data through the National Center for Health Statistics um, surveys from the census or from other large cohort studies. And these can be available to use in additional studies. So this is one way of getting data. You still have to make sure that that's valid and reliable data from your original source. So there's issues with that. It's collected for other purposes. So it may contain unknown issues or biases that we don't know about. Some data may be missing. It may not be exactly what you're looking for. And you have to be concerned about validity. There could be some records that aren't as high, don't have as high validity as some other data. The other thing that you can do is collect new data. So you can do surveys, collecting biospecimens, having people come in for medical exams or visits. And this is great because you can measure exactly what you want to measure with as high validity and reliability as you want, but it takes more time to develop, test, carry out, more expensive, difficult to get people to participate fully. We still have to worry about validity and reliability. If we're doing surveys or questionnaires, we want a tool that's already has that established. Or if when a tool doesn't exist and we create our own questions, you should conduct a validity and reliability study first. Other measures and lab tests should also have established validity and reliability. So sometimes there isn't a reliable and valid data collection, so you have to construct your own. So ideally, you'd test the validity and reliability. At the very least, you'd have experts review them for face validity. And you could also do a pilot test within your subject population and make sure that your questions are clear and accurate. The other thing you might do for your studies, collect specimens or physical exam data. And there's a number of different ways that you could do this. And so you have to think through the easiest way for participants to have that data collected. When you do this, you want to make sure that there's step-by-step instructions, whether you're doing examinations or specimen collections, to make sure that everything is the same and consistent every single time in that collection. So we want to make sure that everything is followed to a specified protocol, and make sure that you have valid and reliable ways of collecting that data. So while we want as much information as possible, we have to limit that data collection to what we truly need and will use for the study. So we want to consider the population and make sure that it makes sense. The data collection that we're using makes sense for this population. We want to make data collection as easy as possible for people participating. And we likely almost always have to consider cost and time of that data collection. So the key things here are make sure you're collecting valid and reliable data and minimizing the burden on participants. All right, so our final topic is assessing differences or data analysis. So when we think about doing data analysis, the methods that we use usually depends on the type of variable the outcome is and the type of variable we're looking at. So if we have continuous variables like weight or blood pressure, we'll use one analysis. If we have dichotomous outcomes like breast cancer, maybe we have an ordinal outcome like a pain scale, so good, better, best, or a time to event like survival analysis or time to disease development. So we have to take those into account. And we also have to think about the structure of the data. If we have longitudinal follow-up data, if we have clustered data, so maybe we're collecting data within families or within schools or within communities. And then we also want to think about how that data was collected or the sampling framework. Okay, so then there's all sorts of different methods based on your data. So if we have continuous outcome data, Um, if we're looking at a continuous exposure measurement, right? So if we're looking at how blood pressure correlates with stress, and we have continuous levels for that, we might do like a linear regression or a correlation analysis. Um, if we have data that doesn't meet our assumptions, maybe we'll do some non-parametric tests. We could do analysis of variance, linear regression. Um, these can also mix in when we have categorical predictors. Um, so those are the methods when we have continuous outcomes. So we usually use something linear when we have continuous outcome data, and we usually assume that that's normal, comes from a normal distribution. If we have dichotomous outcome data, then we have to do something else because it's not linear. So we might do chi-square tests or logistic regression, right? So we are splitting things into groups and looking at how those groups differ, right? Like maybe those with breast cancer and those without. And then commonly we see time to event data. And this takes another special set of analysis where we look at time to event. So we are looking at two things, both the event, yes or no, and how long it takes you to get there. So this middle picture up here shows a time to event analysis. So we look at difference in survival curves. We can do a specific type of regression to do that, or we can do it just looking at two groups. So you have to know what type of data you're using, what type of data is your outcome, what kind of type of data is your predictors, if you need to adjust or control for confounding variables. All of that you have to take into consideration to understand which type of analysis you're going to use. In addition to the basic type of analysis, there's additional considerations as well. If you have longitudinal or clustered data, you have to apply a little bit of a different type of test, or at least adjust for that clustering in your analysis. So some ways to do that, a simple way is a paired t-test, but you could also use generalized estimating equations or random effect models. Another thing to consider is if you have structured surveys, like the National Center for Health Statistics, when they do stratified sampling, you have to account for that with weights in your model. And then if you have missing data, you have to figure out what you're going to do about that. Maybe you'll do multiple imputation. Maybe you'll do weighted models. Even if you do nothing, you're making some assumptions about that missing data. So you have to think about that as well. But the hope is, at the end of the day, you'll have data to answer your hypothesis. So you'll be able to understand if there was a difference in maternal supplementation with vitamin D and type 1 diabetes outcomes. So hopefully you've learned a lot of things about decisions in study planning, understanding that population, how you recruit from it, how to collect that data, and then how to do that analysis overall based on your question and on your data. So thanks for listening and have a great day.